Good morning. Vasu audible ano? Okay. Vasu, Shijit audible ano?
Sir, you are audible. Good morning.
Yeah, Ritvik. Yeah, thank you. Hello. Hi, Ritvik. Hope I am audible, right?
Hello, sir. Yes, you are audible.
We can wait for a couple of minutes. Okay.
Sure.
People are joining.
A very warm good morning to one and all present here. I am Acklin Jojo, Project Fellow NATPAC, and it gives me immense pleasure to welcome you all to the 19th talk of Transpedia Research Talk Series organized by KSCSTE National Transportation Planning and Research Center, NATPAC. This talk series is yet another unique venture of NATPAC designed to explore diverse topics from the cutting-edge technologies to sustainable solutions. Here, we will be featuring eminent young researchers to share their valuable insights for kindling the spirit of future research and development in transportation. Today, we have with us Dr. Ritvik Chauhan, Assistant Professor, Department of Civil Engineering, NIT-Tiruchirappalli, for sharing his valuable insights on the topic to go or not to go, the dilemma during the yellow phase at Signalised intersection. Now, I request Sri Ebin Sam, scientist, to deliver the welcome address.
Thank you. As rightly said, this is our 19th Transpedia talk series where this initiative aspires to create opportunities for young researchers in and outside India to connect, collaborate, shaping the future of research and development in the arena of transportation. Over the past 1.5 years, around the 18 sessions of Transpedia have been successfully conducted, covering a wide array of topics in transportation engineering. Today, it's the 19th talk in the series presented by Dr. Ritvik Chauhan, Assistant Professor, Department of Civil Engineering, NIT-Tiruchirappalli. Let us welcome our esteemed speaker who will share his expertise on exploring the cause-effect method of evaluation and mitigation of the dilemma of drivers at the signalized intersection. We would also like to welcome all the participants from NATPAC and also from various other institutions and organizations. Thank you all once again for joining us. Following the presentation, there will be a Q&A session offering everyone an opportunity to engage directly with the speaker for meaningful exchange of ideas. Thank you.
Thank you, sir, for your welcome note. Now, I would like to invite Dr. Shijit PP, Junior Scientist, to introduce the speaker to the audience.
Good morning, all. Today, we have Dr. Ritvik Chauhan, Assistant Professor in the Department of Civil Engineering, NIT-Tiruchirappalli. Dr. Ritvik received his PhD degree from SVNIT Surat, specializing in the traffic behavior and safety assessment at signalized intersections under mixed traffic conditions. He has more than 6 years of research experience, including the role as a postdoctoral research fellow at IIT Roorkee and project research scientist at IIT Bombay. He has been a part of various sponsored research and consultancy projects involving Intelligence Transportation System, that is ITS, traffic safety analysis, and artificial intelligence and machine learning applications in transportation. His research include the deployment of LiDAR, UAV drones, and connected vehicle technologies for improving the road safety and traffic management. He has received several fellowships and awards from institutions such as MITAX Global, served national postdoctoral fellowships, that is in India, and best paper awards at national conferences, recognizing his contribution to transportation research. His research interests include traffic safety, driver behavior modeling, and data-driven transportation solutions. He has several international and journal publications, and his papers have been presented at prestigious conferences such as TRB, WCTR, and CTRG. With this note, I welcome Dr. Ritvik Chauhan to this talk series. Thank you.
Thank you, sir, for the introduction. Now, I invite our distinguished speaker to deliver the talk. Over to you, sir.
Yes, thank you, everyone. Thank you for the introduction, and mostly thank you to NATPAC for this opportunity, and to Dr. Vasudevan also for this invitation. I'll just... Is it visible?
Yeah, it's visible. Can you make it a slideshow mode?
Yeah.
Yeah, perfect. Thank you.
Okay. So, good morning, everyone present here. My name is Ritvik Chauhan, and I'll be presenting this 19th talk of the Transpedia Research Talk Series. My title would be To Go or Not to Go. This is a specific topic that I have already worked on during my PhD and the extended work that was carried on during the postdoctoral work. And also at present, one of my students is working. I'll be presenting what are the insights that have been obtained, what are the current progress in dilemma zone evaluation in predicting the decisions of the drivers, and what are the future scope that we can work on. Mostly the presentation or the talk would focus on what are the phases, basically not in this specific order, but we will focus on what are different phases of signalized intersection, what is dilemma and dilemma zone. If you want to study dilemma zone, what are the requirements, what are the different means of evaluation and identification, how the safety is, what are the safety aspects during the dilemma zone, and what are the potential means that have been employed till date for mitigation of dilemma zone. So I'll just briefly go through this, that signalized intersection is just one of the traffic control parameters that we employed to provide a safe maneuvering for conflicting traffic stream. At junction, whenever there are more than 2 or 3 conflicting streams, we employ different type of traffic parameters, and signalization being one of them. However, globally and even in Indian records, if we follow through that, significant number of road accidents have been observed. But why is it so? Means even though road control parameters are observed, the main reason have been observed because of high speeding, red light violations, and mostly the rear end collisions that are occurring because of the vehicles that are stationary at the signals intersection. We generally observe 3 phases at signals intersection, and their functions are pretty much clear. Red phase, that the vehicle should stop. Green phase, the vehicle have the right of way, or that specific approach has the right of way, and they are allowed to go. And amber phase, that succeeds the green phase and precedes the red phase, is to provide a warning to the drivers that a imminent red phase is there. Please decelerate and achieve a stop, or if you are already at the stop line, you may please continue and clear away from the intersection. However, in India, it is generally observed that to avoid additional delay, the drivers often tend to cross even during the amber phase. And that means, as it's observed in most of the developed countries, the policy or general rules that are followed as go at green. That means if it is green, then only the drivers are going. But we over here, we observe stop at red. That means as long, if it is red, then only the drivers tend to stop. If it is not red, the drivers pursue that as a permission to cross the road. And because of which, even during the amber phase, people or the drivers do continue to cross the stop line until it does not turn red. What are the results of this? This creates a certain scenario where, even as we can see over here, if it's red light, even if the red light has just turned out, whatever vehicle had crossed the stop line, they are occupying the intersection width, because of which the next approach that is supposed to receive the right green phase is not able to traverse through the intersection. So coming back to our amber phase, it serves as a buffer zone. A buffer zone, so between 2 consecutive green phases. But in many instances, a driver is often observed to be unable to decide whether to stop or go during the dilemma phase. And this delay in the decision or this dilemma zone often results in either aggressive deceleration, if it is sudden red, or red light violations also. And the consequences are rear end collisions or side impact from the next traffic stream that is receiving the green phase. So the question that raises is, can we somehow predict as to what will be the driver's decision, whether the potential driver will stop or go? And secondly, can we provide some assistance or some measures that will help the driver to decide whether he should stop rather than going? Towards this, we perform dilemma zone analysis or prediction of driver decision. So dilemma zone mainly occurs in the upstream region. Let's say at this signalized intersection, this red line I'm drawing is the stop line. and this is the direction of the traffic. So the dilemma zone will potentially occur on the upstream zone. Similarly, for opposite stream, it can be on the other side. So if we are able to accurately identify this potential dilemma zone that we are observing, we can provide some means of indication to the drivers that this is a potential dilemma zone. If there is an amber phase, it's better that you decelerate rather than ending up in harsh deceleration, aggressive deceleration conditions, or red light violation conditions. So over the studies, it was observed in 1960. And it was observed that there are two types of dilemma zone. The first type of dilemma zone that we see over here is based on vehicle characteristics or the physical and operational characteristics. That means with the speed that the vehicle is moving at, the vehicle will neither be able to stop before the stop line, nor it will be able to completely cross the intersection safely in the given amount of time. So if it is not able to stop before the stop line, nor it is able to cross the intersection, it will end up in the region of intersection. That's what we call it as type 1 dilemma zone. Second type of dilemma zone is a type 2 dilemma zone, where driver, considering multiple factors, decides on his own, or he perceives that he can safely cross the intersection or he can safely stop. But if he is not able to decide, that results or that dynamic result from the dilemma, from the driver's decision, is termed as type 2 dilemma. So type 1 dilemma, how do we measure? Since it is based on vehicle characteristics, we consider as to if a vehicle is arriving from this point, it needs a certain point of clearance. That means the particular vehicle should cross its particular distance to the stop line along with the width, and such that not the front part of the vehicle, but even the latter end or the rear bumper should cross the intersection. So whether the vehicle has clearance distance, possible potential clearance distance within the available time before the red turns on, or else from the position of the vehicle, if it starts decelerating at normal rate, will it be able to stop before the stop line or not, is what we see. So whether if it will be able to clear, it can cross safely. If it will be able to stop before the stop line, it will stop. But if it is neither able to clear nor able to stop, that region we call it as dilemma zone. There is another option, that if whether the driver has an opportunity that it can either safely cross the intersection or safely stop, that we call it as option zone. However, in India, among multiple studies, it has been found that option zone rarely occurs. But if we want to provide option zone, it's very easy. What the theory states that we need to calculate the stopping distance, that is braking distance, and the crossing distance, in which width of the intersection, length of the vehicle, time available before red starts, and the reaction time is considered. So since speed is restricted till maximum speed limit, let's consider deceleration rate also as comfortable deceleration rate. Reaction time are constant. Width does not change. Length of vehicle for that particular category does not change. So the only thing that can be changed is time to red. That means if we want to eliminate type 1 dilemma zone, as the studies have cited over here, that it can be eliminated by proper signal timing design. So we need to improve time to red more. That means either the best potential solution would be to increase amber time as long as it possible, so that to provide either the option or reduce the length of this dilemma zone. But as I said earlier, we follow stop at red, or we observe stop at red policy. So till what point can we increase this time to red or amber time? It has to be restricted, and generally it is restricted between 3 to 4 seconds. So that is a limit of type 1 dilemma zone. That means type 1 dilemma zone cannot be properly eliminated in Indian condition. If it is required, if it needs to be eliminated, it has to be followed by proper traffic rule for adherence by the society. Second is type 2 dilemma zone. So type 2 dilemma zone, since it's a decision of the driver makes that decision considering multiple parameters that it considers as to what is the vehicle speed at the start of amber phase, how far is the vehicle from the stop line, and what type of vehicle is moving, or what type of vehicle is the driver driving. These are the three main parameters that were used in the earlier studies and in most of the studies. However, there are multiple studies who have found that in addition to these three, there are many more parameters which are found to be significant that are related to the vehicle. Vehicle characteristics, the signal operation characteristics, field geometry or environmental characteristics, the driver parameters, what type of traffic conditions are there. The studies have been carried for different traffic conditions, and different methods have also been utilized. So since these many parameters have been found to be significant, that brings a probabilistic nature to the type 2 dilemma zone. So where type 1 was static, type 2 is stated to be dynamic or probabilistic in nature. And hence, since it is probabilistic, studies have carried out on data-driven techniques to calculate what might be the potential probability of a vehicle opting to stop or to cross considering its different parameters. So since the decision is binary, whether the vehicle should cross or vehicle should stop, binary logistic regression has most widely been used, in which we consider multiple parameters, as we have seen in this table, to be as independent parameters, and my dependent parameter would be decision to stop or cross. Similarly, based on this utility equation, we can find out what will be the probability of passing or probability of stopping. It depends. If you are modeling for crossing, then you will get P of passing based on the equation, and 1 minus probability of passing will give you probability of stopping. If that you can calculate what will be the probability, this left side image that you see, this is the plot type of figure that you will get from the data, provided that you have considered multiple points. However, if you consider a constant value for all the vehicles, a particular speed, a distance, and multiple parameters that you have considered as independent, you get a single line that we see in this plot over here. And in this plot, type 2 dilemma is said to be the region between 10% to 90% stopping probability. These are the majority studies that have recommended. Some studies have also gone from 85 till 15 percentile, between 15% to 85%. Some studies have also gone between 20 to 80% stopping probability. But whatever this region corresponds to in distance, it is said to be the dilemma zone where indecision or delay in the decision making occurs. And subsequently, as we saw for type 1 dilemma zone, the region considering an average speed or the speed limit of the intersection, which is the region where a vehicle particularly arriving will not be able to cross or stop, will be under dilemma. So this is the visualization. The figure you see on the top, we can bifurcate this in half. The left side indicates what are the type 1 dilemma zone, and the right one indicates type 2 dilemma zone. Now, type 2 dilemma zone, as we saw in previous figure, this was based on distance from the stop line. Some studies have also gone with temporal dilemma zone. That means between 2.5 second to 5.5 second is where, before time to red, is where the dilemma in decision making is often observed. But if we want to calculate temporal based dilemma zone, there should be an indication to the driver as to, let's say, time limit or green time that is available. We have display counters, countdown timers at signalized intersections. If those are available, then based on the values from them, it has been found out that 2.5 second to 5.5 second is an acceptable region where the dilemma will occur. Subsequently, based on our stopping distance and crossing distance between type 1, we see that this figure dotted line represents the crossing distance. And that means if anywhere it is below this region or below the blue line, a vehicle can easily cross. And the red line indicates the stopping equation line, stopping distance equation line. So if the vehicle is above that, the vehicle can easily stop. That means this region that you see bounded between the two lines is our option zone. And after this is where our dilemma zone occurs. Because of the stop at red policy, the result that we see, I can choose another color. Yeah. In Indian condition, when we studied the same plot, we found that XS might be a certain curve, but our stopping line is like this, because of which option zone does not exist, and this entire region is found to be completely dilemma zone. So now since we have studied as to how to estimate a dilemma zone or what are the potential methods, how do we collect the data that helps us analyze it? First of all, if you have the vehicular trajectory data, that is the most helpful, because trajectory data provides us with in-depth, even to the microscopic level, what might be the potential driver behavior. And based on that, we can estimate it. But for that, if you want reliable data, some key considerations you please remember, such that you try to calculate video from as high vantage point as possible, so that every vehicle is visible individually, considering the weak lane discipline traffic. As you see in this D plot, not all the vehicles are traced automatically. Even if you want to trace them manually, you need a large screen monitor and properly zoomed in or high resolution video camera, so that you can point accurate positions of all the vehicles. But this is what the studies are following today. Earlier, what it used to be. Before, in this present study, the data was extracted using trajectory data, but I have, for representation purposes, I have drawn this red grid patterns, if you can see, on all the 3 study locations. So earlier, as soon as the signal phase turns orange, that based on video on the signal cycle length, all the researchers know. As soon as it turns orange, they mark the position of a particular vehicle, at what point that particular vehicle is from the stop line. That means all these grids, lines that you see, will have a specific distance, and the time difference it requires for that vehicle to cross 2 grids will give us the speed of the vehicle and the location. So we have the speed of the vehicle, we have the location or the distance from the stop line, we know the vehicle category, and as an additional parameter, we can consider which lane the vehicle is moving in. Okay, so we have the main parameters that have been found significant from the earlier studies. And if you have the study location data, you can consider additional parameter, whether does the type of intersection is playing a significant role as a categorical variable. Is the approach road width or the number of lanes significant? Is the cycle length, considering if the drivers are acquainted with the signal intersection, he knows the signal cycle length and the delay it might cause. So whether the signal cycle is a significant parameter, whether the amber duration or the green duration is significant or not. These are the multiple parameters that if you wish to add to your analysis for type 2 dilemma zone, you can add them. So in our study, what we considered multiple parameters. Firstly, we developed 2 models. A simple model that only considered distance from stop line, longitudinal speed, the vehicle type, and the lane in which the vehicle was moving. Lane number, and I think type of the vehicle over here, it's not specified. Yeah, it is not given over here. And the second model, we considered all these parameters that you see in this table, just to check whether consideration of more parameters, does it yield better result? Of course, if you have more data-driven techniques will yield better results, but that depends whether you can acquire this data. Over here, trajectory data proves its advantage that since you have the trajectory data, you can extract all these parameters, considering what might be the potential location of the vehicle, lateral location of the vehicle, which lane it's moving, whether it is undergoing lateral movement, then what is the signal cycle length, whether auxiliary lane was present, acceleration of the vehicle can also be considered. So based on that, we considered a simple model using only 3 of the parameters: speed, distance, vehicle type, and lane number. We found out on external validation, considering an additional study location data, that we had an accuracy of 70%. Okay, there have been studies also, other studies also, that have some accuracy. So at present, let's say the studies in India have achieved 70.28% accuracy of predicting whether the driver will stop or not. If we add additional parameters, all the parameters, we are getting accuracy of 79 or almost 80% on external validation. But if that model that is developed is used for the same intersection, we have 90% accuracy. So let's say this is an acceptable value. And with that, we are sure that with 90% accuracy, we can predict whether the driver will stop or go. Where the model helps, the regression-based models, since they give us coefficients and parameters, they help us in evaluating different policies. What if we increase the speed limit, or what if the overall average speed of the traffic increases? What if the vehicle is found to be accelerating at the intersection? If the lateral movement, let's say motorized two-wheeler undergo more lateral movement, whether the vehicles are shifting towards median or they are laterally shifting on the road. What if the vehicle size is increasing? Based on that, how the dilemma zone shifts away from the signalized intersection or near the intersection. This can be studied if you have a regression-based equation. And this helps us in pinpointing the accurate location where the dilemma might occur to the driver at particular intersection. And based on that, if you have type 1 dilemma zone that you have marked, or type 2 dilemma zone, such sort of markings are provided at intersection, so that to guide the driver that this is a dilemma zone, please make your decision before you cross over this region. This might be the safe limit, upper boundary or lower boundary, where you might be able to safely slow down or cross. If you are after this zone, please cross as soon as, provided that this turns amber right at that time. Or if you are before this line, please stop. And if you are in this region, the probability could be, or the most desired option should be, to either stop so that you can achieve a safer crossing rather than going with the red light violation. Now the next aspect is whether if the driver, even after providing these means, ends up making a wrong decision. What might be the potential options? First is he can decelerate very hard. If it is decelerating very hard, he is ending up with a rear end collision. Okay, and because of that collision, how do we measure that? So we have different proactive safety assessment. If we rely on accident data, the problem would be at one location, every location, what was the potential reason of accidents, and whether the number of accidents were sufficient to provide a safety improvement measures are adequate or not, whether that would be properly justifiable or not, it's difficult. So hence we study, in this present study, we went with proactive safety assessment. We used surrogate measures to detect the conflicts. And based on the conflict, we found out what are the hotspots. We tried to model the rear end conflicts as to what is the probability that with given parameters, what is the probability that a particular vehicle will end up in rear end conflict. And if we just change simple traffic operation parameters, can we reduce the probability of rear end conflict for a particular vehicle? So what is a conflict? I'll just briefly go through this. If two vehicles are moving, provided that the follower is traveling at higher speed than the leader, then at certain point, there is a potential that they will occur in a rear end conflict. But if during that moment, if the driver perceives and it decelerates at some point and change the trajectory, then the conflict point is avoided. So this surrogate safety measure considers that the potential collision will occur. And another theory that every accident was a conflict, but every conflict is not an accident. So if you can remove a conflict, there you can entirely remove an accident. That is basic essence of what we go with surrogate safety assessment. We use two surrogate safety measures, time to collision and deceleration rate to avoid collision. Basically, at what rate should the vehicle decelerate to avoid the collision? And if the vehicle continues to move at the same rate or same speed, after how much time will the vehicle collide with another vehicle? So based on that, we found out what might be the potential leader, follower, or vehicle that are interacting with each other, or potential interactions between each other, and what were their relative speed, the delta x and delta v, and based on that, whether they were in conflicts or not. And we found that on the curve side, the conflict zone or conflict propensity is higher near the stop line, and as you move towards the median side, the conflict heat zone moves away from this. Potential reason might be, it was another reason that this area near the curve side was mostly observed to be occupied by motorized two-wheeler, and another area on the median side was observed to be occupied by bigger vehicles, car or LCV. And since these vehicles are either more cautious, or they require more level of deceleration, or they have lower maneuverability, their decision might be much more before the signal stop line, that is at 0. And whereas two-wheeler, because of their high maneuverability and some sort of advantage because of the road size, were observed to be, other than more aggressive, they were also observed to be decelerate at higher rate near the stop line, because of which the potential of rear-end conflicts was significantly higher near the curb side, where two-wheeler vehicles were found to be more. Second is, if you have, now we have identified what are the potential hotspots, how can we model them? Whether between every two vehicle, nowadays we are seeing collision avoidance system, advanced driver assistance system, that is basically using time to, let's say, safe distance a vehicle should follow, or time to collision, or some advanced surrogate safety measure. And they predict that with this speed, if the radar detects there is an obstruction ahead or another vehicle ahead, how much time it has before the collision occurs. It will have a cutoff threshold. If the cutoff vehicle is in much near category than the threshold, it will decelerate. Similarly, for rear-end conflict, what we did was considering those thresholds, we had identified the conflicts. Now, for that conflict, what will be the probability? And secondly, what will be the number of rear-end conflicts? If we can predict based on the operation conditions, what are the number of rear-end conflicts, it has practical applications. This is one of the practical applications. We can determine what are the potential hotspots for our current operation policy, and whether a change in policy will result in change in number of conflicts or not. For rear-end conflict probability, that provides advanced driver decision-making assistance, or it works on microscopic level. So, like decision, since our decision is binary, to stop or to pass, the conflict is also binary variable based on the different independent parameters that we have considered. Whether it was a conflict or not between two vehicle classes can also be binary, and hence we also use binary logistic regression. Now in this, we use multiple parameters. We use the longitudinal speed of the vehicle, leading vehicle, following vehicle, what was the follower location, was there any lateral overlap between the two vehicles? Let's say this is one vehicle and this is another vehicle. So a particular region would be the lateral overlap. And because we don't have lane discipline, this particular vehicle can deviate on the right side and can also overtake. Hence, we also consider what was the lateral overlap and does it have a significance. What was the follower's lateral speed while moving? So that means if it is laterally moving since initially, that means he can easily overtake, or it can negate the lateral overlap. What was the leading vehicle class and follower vehicle class? In addition to that, since the data was already extracted, we had whether the leader's decision to pass, or what was the leader and follower's decision. Based on that, using different surrogate safety measures and at different thresholds also, we tried to model as to what will be the conflict probability. And as we can see in the red fonts over here, that even the decision of the vehicles were found to be significant among other parameters. That means, considering with the advancement of technology, let's assume a simple case scenario that intelligent transportation system exists and there is vehicle to vehicle communication at this intersection. So if we can provide a following vehicle that the leading vehicle has decided to stop or decided to pass, please take your decision, or your decision should be based on that. The leading vehicle is stopping, please stop. Does it change the decision or not? So as I earlier showed you, this is the data that we get. 0.5 is set as the threshold for stopping probability. That means if your probability is obtained to be more than 0.5, the decision would be stop. And if it is less than 0.5, the decision would be to cross. And we see from over here that multiple vehicles that should be stopping are actually crossing, and that should be passing are actually stopping. So there are wrong decisions undertaken by the vehicles. Okay. Now, if we say that using this particular model, we have communicated a vehicle, a particular leader vehicle decision, whether it will stop or pass to the follower. And then it changes the decision based on the leader's vehicles. We found that for all the vehicles, there was 11% reduction in the rear end conflict probability, or means the probability that they would be in the rear end conflict was reduced by almost 11%. Only based on single that if the following vehicle adheres to the suggested decision. And if the leader and follower, that means the leader is given a decision that you cannot safely cross, please stop. And the leader is stopping, that decision is also conveyed to the following vehicle. The reduction in rear end conflict probability was observed to be 15.74%. Secondly, let's come to the real time now. If we want to provide such sort of solutions to the drivers, a driver decision assistance system during dilemma, we need real-time decision prediction. And that nowadays we achieve using machine learning techniques. So for the same data set, we created 4 models. We wanted to check in model A and model B, we only use minimal parameters of speed, distance, and vehicle type. Model B and model C. And in model A and model C, what we considered was we used all the parameters. In first 2 models, we have split them in 70 to 30%. And in last 2 models, we used 3 study section data for model development and one study section, the 4th study section for model validation. So we try to check 2 things. Does inclusion of more number of parameters improve the accuracy significantly? Or rather than that, let's consider the minimal number of most significant parameters to reduce the computational load and reduce the prediction time of the model. And with the lesser number of parameters, if you are getting the accuracy or not. Secondly, should we develop a model that is consideration of parameters from all the study location, 70% for model development, and then use 30% for splitter? Or is external validation required always? So based on that, we use multiple regression machine learning model. Mostly 5 models were used, but the best results were achieved from SVM, support vector machine, decision tree, and random forest. In this random forest yielded the best results for 70-30 split, or let's say the models that had all the parameters. But if we went with only less number of parameters, we found that the decision tree was also working very well. And since with less number of model, also with for 70-30 split or external validation, internal validation or external validation, we found out the results were almost similar. That means irrespective whether you go with internal or external validation, models with less number of data and that constitutes data from multiple study locations so that all the intricacies and complex relationship between the parameters is obtained or not. If that is considered and the model is developed on those parameters, we can develop such decision tree models so that accurate prediction of driver's decision can be undertaken as to whether the driver will stop or driver will pass. Where this model will be useful? Okay, I'll come to this result again. And unlike regression equation, as we studied for binary logistic regression, it provides us coefficient in which we can check as to which parameter is significantly affecting or not, and what would be the change in magnitude in the dilemma because of that. However, in machine learning, we are restricted by that. We do not get as to what will be the potential effect. We only get a parameter that we identify using Shapley value or also variable importance. This is Shapley additive variable parameter. This provides as to whatever independent parameter you had used. Let's say distance, speed, average acceleration, lateral speed, or just 3 parameters, distance, speed, and vehicle. What was their effect on correct prediction of stopping or passing? And if we see the beehive, we see as to their effect on prediction is very low. The blue color shows very low, or the effect on prediction is very high. That means positively affecting and very high, or negative prediction is very low. So we can only find out what is the effect of parameter or which parameters are significantly contributing towards more higher accurate prediction. So remember the plots I showed you earlier, the results that I said I'll come back to over here. So currently what we are working on is we are trying to develop a framework that takes advantage of intelligent transportation system and an assumption that a vehicle to infrastructure communication exists. So if this exists, can we provide certain means in which the driver can be alerted and can be guided to take safe decision, a decision that provides him safe maneuverability during the dilemma or the intersection. So we know, or since we have studied, we have identified type 1 dilemma zone, we have identified type 2 dilemma zone. Additionally, what we went is we found out the overlying area where type 1 and type 2 dilemma zone both occurs. And we have termed at present, this is not an official term, over here for this presentation or this study, we have termed it as a critical dilemma zone. That means whatever decision assistance system is to be provided, the priority is that at least in this zone, the decision should be communicated to the driver. As to how we do that. So from our trajectory data or the field data, we will be able to gather some distance. What is the driver's time that is required to reach the stop line based on its speed and distance? What is the time that is left in green or the yellow time that is left? In addition, that means time to red that is available to us. So whether that is safe, no, unsafe, no, it is not unsafe, maintain the current speed and cross. Or if it is unsafe, yes, please take a decision to cross or stop. So what we have achieved is we have achieved type 1 dilemma that the vehicle should take considering its movement. Secondly, based on regression equation at higher accuracy, 90% or 85%, or let's assume that at present highest accuracy is achieved. We can predict what will be the driver's decision. So our suggestion was based on type 1 dilemma, he should cross, the vehicle crossed. Okay, the vehicle that should cross has crossed. It's a normal crossing decision. It will undergo no signal violation and no safety hazard also. But if a vehicle that should cross had stopped, so what it is? The vehicle should cross, but it stopped. That means it underwent an abrupt stopping or deceleration. There was no signal violation, but there is a chance of rear end collision. Similarly, for a vehicle that are stopping but should cross, or vehicle that should stop are crossing, that means they are undergoing aggressive crossing, acceleration, and there might be a signal violation observed. and chance of rear angle collision. So these we can predict, and based on trajectory data, if we have the trajectory data, this can be predicted completely. So if we can predict this, so that means whether the vehicle will undergo normal crossing, abrupt stopping, or easy crossing, aggressive crossing, aggressive stopping, aggressive crossing, or normal stopping. We can also predict those decisions if we have the parameter. This plot shows, apologies for this, that the vehicle cannot stop, the vehicle can easily cross, or it can easily stop. At present, the data we had was only for these three parameters. So these three we can predict. So let's say he cannot stop. This category is crucial for us, that the vehicle won't be able to, he cannot stop easily. That means he will end up in the dilemma zone. So what can we do? We have a data set. We have all the parameters that are considered. Based on that, what is the stopping and clearance distance required, whether the decision should be to stop or cross, whether the vehicle should be in dilemma or option zone, or do you wish to suggest it? So based on that, the suggestion, whether dilemma or option, we suggested whether the vehicle should keep on going, keep on stopping based on the parameter. But for a particular vehicle that is in dilemma, what can be done? We have the trajectory data, we will keep on analyzing. So that means, let's assume if a vehicle was moving at a continuous speed and our calculations yielded that at certain point, that vehicle is going to be in dilemma, and such a dilemma that even if it accelerates at comfortable threshold of 3.4 meter per second square, it is not able to safely stop, safely cross, or if it's decelerate, it is not able to safely stop. If it has to accelerate at 5 meter per second square, it cannot safely stop. That means it has to decelerate at 5 meter per second square to safely stop. So that means our suggestions yields that if the vehicle continues at its own speed and threshold, it will reach a dilemma in which the vehicle will have to undergo harsh deceleration, that is 5 meter per second square, which is not comfortable. So that means what is the last point till the vehicle where it can easily stop or easily cross the section. We will identify that particular point, and at that particular point, we will suggest some decision to the vehicle based on this parameter, whether he should cross. Over here we have whether he should cross or he should stop rather than the decision. And that can be provided using simple means as just a blinker on the dashboard, or just a simple chime, because studies in advanced developed countries have already been following this. Just a simple indicator, a green indicator that please accelerate or please continue going, or a red indicator that you should stop, so that you can traverse the intersection safely without facing the dilemma. So based on this, I'll conclude my talk for today. We have identified that at present, with the studies that have been conducted in India or for our particular mixed lane traffic conditions, that the indecision in the drivers during the amber phase can lead to dangerous situation. But accurate prediction of dilemma zone or the driver's decision is possible. And if we use data-driven techniques or a significant amount of data that encompass the driving behavior, operating conditions, and traffic behavior from multiple locations, the model can be developed that is able to predict the driver's decision. That helps us to identify what are the potential dilemma zone. If we go for lane marking, it can be a static safety measures for driver assistance. If we go for vehicle to infrastructure communication, that could be a dynamic driver assistance system. And these methods will help in enhancing the safety. Lastly, since at the start I said we observe stop at red policy, if only we all could adhere to go at green policy. That means if it is green, then only go or accelerate. If it is anything else, the first instance should be to decelerate and stop. That would help us in avoiding these conflicting scenarios. Thank you very much. These are some of the references. If need be, I can also share them via Dr. Vasudevan.
That was an informative session. Thank you, sir. Now the forum is open for discussion.
Hello, Dr. Ritvik. It was a good presentation. Thank you for this informative one. I had a few doubts.
Yes, sir.
You were showing one figure in which you had shown a box marking. Is that something that has been adopted somewhere, or it was just an indication that this is the dilemma zone and has to be communicated to the driver?
This
Because
box
as I
mark,
understand,
okay. Understood. Just a second. I think that was in type 1 dilemma zone.
the marking
This
is
box
actually,
marking, sir?
I'm not able to see the screen.
Oh, sure. Sorry. Yeah, I hope it's
Yeah, this
visible
one.
now.
Yes.
Yeah. This study that you see on the right side, this was a driving simulator study. But at present, on field, there are multiple locations in Europe, and also some cases in India have been observed. Some local traffic authorities that have started implementing marking of these signs.
But box markings are a prohibitive marking, so it is given at locations where you're sure to actually exit from the other side. So if this is given for a dilemma zone, wouldn't that be counterintuitive?
Yeah, that is another issue. The counterintuitive would be if we also go for driver assistance, like we see in the lower diagram, yellow impeding, please slow down. This is also a distraction for the driver. So whether the driver assistance or this sign are counterintuitive or not, that is another policy measure that has at present yet not been studied. The studies are only focused on what are the potential means with which we can help to reduce the dilemma, how they can be integrated in the field with the existing rules and guidelines is yet to be studied, sir.
Okay. And what about the approaches? Do you have any locations where you have a free left or a pedestrian crossing also happening? Because that will add to the complexity of what you're trying to achieve.
Yes, sir. That will add to the complexity. I think in the study locations we had two study locations had free left turn. Yeah. Two study locations, A and if you can see, C had free left turn with proper auxiliary lanes design, whereas B did not have free left turn. There was crosswalk also with pedestrian movements occurring, but at present we did not study the effect of pedestrians. We studied the effect of crosswalk being present as a categorical variable 1 and 0, but with the volume of pedestrians that are moving through that, whether that will affect or not, that has not been studied.
Okay. And you were also mentioning about the countdown timer.
Yes,
Uh,
sir.
If if we don't give the countdown timer, will it have any significance? Because of only knowing the time that is left, people are accelerating at the dilemma zone.
People are accelerating. Countdown timer were provided with the hope that they will warn the drivers that red is impending. Please start to decelerate. But a study from CRR, I think Satish Chandra sir and the principal scientist, Will Murugan sir, they had conducted one study in which the result was found to be totally opposite. All the drivers or almost majority of the drivers were observed to accelerate during the end of phase or end of timers.
Yes,
So
exactly.
provision
So,
of that would be effective or not in Indians for the Indian driving condition. It has been proven that that is not effective. That is in fact resulting in more aggressive driving or increase of acceleration at higher speed driving of the vehicles.
yes, so
My
practically
comment was
also,
only from the scenario of type 1 dilemma, whether can we completely remove type 1 dilemma by providing that. But for Indian condition, as of now, that has not proven any helpful, sir.
okay, one last question. Do you have you observed any scenario in which a smaller vehicle, might be two-wheeler, is following a larger vehicle, a bus or a truck or something? so he's not able to view what the uh,
I
light is,
have that.
traffic signal. So that will also cause the rear end collision. So has that been taken to consideration?
Yeah, that has been taken into consideration. If I may, I'll just bring one image for you. Not exactly this, but if you can see this image, this was at Ahmedabad. The leading vehicle decelerated very fast at the amber time, and because of which there was at the rear end, left-hand rear end, the two-wheeler had decelerated. Later on, we found out that this two-wheeler took a right turn also. So an entire video clip is available. There was another study in Surat just recently conducted, in which two-wheeler ended up colliding into a LCV, the small light commercial vehicle we have, 207, Tata 207, I think, in that. So because of, if the visibility is not there or because of close vehicle following behavior, that has been an ill effect.
Okay. Thank you.
Good morning, sir. Am I audible?
Yes, Dilipan.
Yes, sir. Sir, my doubt is like you talked about SHAP shape values, right? Can you tell a little more about it? I didn't understood that part.
See, I'll just, as a base primer, I'll bring it over to this table. These values that we see, these are the coefficients that we get from regression equations. So if we substitute these coefficients, we can get what is our final dependent parameter. And the plus value or the minus value also shows whether our decision or the dependent variable will be positively influenced or negatively influenced. And the value shows by what magnitude. However, for Shapley or in machine learning, the problem is we do not get such coefficients. We only get the impact on the model output or impact on our decision or the final prediction. So let's say there are two predictions. Blue signifies stopping and red signifies crossing. So what is the impact? I can bring your attention to, this beehive plot that you are seeing, the B plot. Okay. Shapley additive, what it says is whether the impact on the decision prediction is high or low. That is given by color. Blue color says that the impact is very low. Red color says that the impact is very high. Now, the magnitude of these values, this specifies whether by what magnitude will that affect be towards the decision. If I can plot out, okay, I cannot plot out, but I can share you a simple wording PDF with all the explanations.
Sure, sir.
But if I have to repeat, at present, final Y, whatever our decision is, we cannot say what will be the probability or what will be the decision based on this value. We are only able to get what is the effect or the magnitude of the effect on correct prediction. Whether it is negative prediction or false prediction or right prediction, and whether the prediction effect is very high or the effect of correct prediction is very high or very low, that is only what we are able to get from machine learning. We are not able to get the magnitude or quantification.
So
just
on
for
all
checking
three models,
which parameter is significantly affecting or not. That is all.
So on the three models you mentioned, that one also. So support, vector, machine, decision tree, and random forest.
Yeah.
Okay.
In that SHAP value are for random forest model.
Okay.
These are for random forest model. Since we had both the models, decision tree and random forest, both as good prediction, so in the study we developed a decision tree that helps us for prediction and which parameter is significant, we gave over this. So since if you can see this C plot at the top, we see that crosswalk, amber, auxiliary, display timer, G by C ratio, the type of intersection or the carriageway width had no effect on accurate prediction of my decision in C model. So these parameters we did not rely or use these parameters. Hence, we can also reduce the complexity or computation load on our model.
Understood, sir.
Yeah.
Thank you, sir.
Sure. No other questions?
Good morning, Dr. Ritvik. It was a nice presentation. This is Dr. Praveen from NATPAC. I have a small query, like it's a bit of doubt, like what's the effect of travel, like time pressure, like was like it's whether the peak time or the off-peak time was taken into account? Like for example, normally this dilemma zone and the decision made by the drivers can be due to the time pressure. For example, during the early morning, during the morning rush time, like during the office timings or something, they might.
Yes, sir.
Yeah,
Understood. The effect of time pressure to reach at their destination at as fast as possible if they are delayed or not. So I think there was a study in IIT Bombay, Nishant Pawar, at present he is faculty in NIT Calicut. His PhD is focused on time pressure. And what they studied was during time pressure, two aspects were critical, clearly observed. That there was significant reduction in the reaction time, or the reaction time, although not significant, was found to be reduced compared to other normal instances, and the vehicle were driving more aggressively. So based on that, if we are to incorporate the effect of time pressure, what we would see is increase in the operational speed more than the speed limit, higher rate of deceleration, potential higher rate of deceleration, and lesser reaction time, because of which we know our type 1 dilemma zone will change. Secondly, for type 2 dilemma zone, if it's in the time pressure, irrespective of that, even if it is just 1 second to red, a vehicle will and tend to, there are those plots. Yeah. Vehicle will tend to cross. That means irrespective of that, let's see over here, these vehicles. Yeah, I think this should be much better. These vehicles, you see on the top, the two red plots of these data points, these vehicles technically should stop, but they ended up passing. And this is totally away as an outlier from the entire cluster of the data set that we see. So this is what a potential effect of time pressure can look like on our data set. This is not the actual reason, but if it was, this is what I'm referring to, that this is where it might look like in our data set, sir.
Okay, so like what was the time of data collection? Like was it for the peaker or off peaker? Like these two are standing out as outliers, right?
Yeah, these study locations were all considered during off-peak hour, because to check the adverse effect of the dilemma, we had to consider under saturation conditions, and under saturation conditions are less likely to happen during peak hour rather than off peak hour, because if it is oversaturated or saturated condition, the dilemma zone is observed to be almost negligible or near the stop line only. And the speeds are also very less, because since the queue is not able to dissipate completely, vehicles are not reaching their desired speed. So the effect of speed, the distance from the stop line, is rarely observed. And secondly, if it is during peak hour, if there are saturated condition, till the last moment, people will tend to go because of the herd mentality. all the vehicles are moving. Because of that, whatever vehicle can go will go. That effect would be observed in clearance time, the lost time, time lost during clearance time for signal designing. But in dilemma zone, that was not very helpful for peak hour or saturated conditions, sir. So all the study locations were under saturated conditions only.
Okay, so I believe that is like normally was there queue duration queue formed during the data collection, or was it like both queued vehicles and through vehicles were taken uh, as a common group and did the analysis?
No, sir. During the red phase, there was queue generation at intersection.
Okay.
But during the green phase, the entire queue was dissipated entirely. Plus some additional vehicles that are arriving from far upstream point were able to cross the junction before the green turned red. That means whatever vehicles were arriving from upstream, far upstream area, they were able to traverse to the intersection at their desired speed also. And
Okay.
queue length, maximum queue length, I have given provided over here. Okay, in this data section, I have not provided. But maximum queue length, what was observed are varying for all the signal cycles. That means degree of saturation was different, but all were undersaturated. That was for sure.
Okay, just one more question. Like you were mentioning that the signal cycle length is probably one of the factors which might govern the elements. Like, but as I've seen that in your data collection, the three locations, like one was around 119 seconds, another around 130 seconds, and another around 220 seconds, right?
Yes, sir.
Signal cycle. So,
yeah.
But like as per IRC, it should be around 120, right? Or
130,
yeah.
Location, USF should be 130 seconds. Yes, sir.
Yeah, but the two intersections were more or less nearer to that values, but the third one was almost nearing the double. So
200, yes, sir.
yeah. So have you done something like some analysis, like whether this thing, like it's a longer cycle length, have anything to do with this thing?
No, sir. As of now, whether then that would mean I will need to calculate what is the average delay at all the study locations and whether average delay to the vehicle is also affecting their decision or not.
Yeah.
But that needs to be correlated with the previous cycle, what speed and when they arrived, and in the next cycle when they left, or whether if this is the average delay that is occurring at the intersection, considering that the driver is acquainted with the intersection to avoid that additional delay, is he driving aggressively or not? That would be a very case specific location, or no, it can be considered. But no, sir, we have not considered that aspect in this
Okay,
study.
so like you have mentioned that signal cycle was being considered. So how was it being, cycle length was being considered? Signal cycle length was being considered in right in one of the slides. I think various, you have listed the various parameters which might
we have considered just a signal cycle length at that particular signal cycle length. If that is of the modeling, whether it is significant or not, we just considered all the parameters operational vehicles, since from the studies we had found out that all the parameters, where is it? Yeah. Regarding signal operations field. So we tried to consider them. Some area we found them significant, whereas in some location, as we see G/C signal cycle length, their effect is not significant.
Okay, fine. Okay. Fine. So I believe like the data collection was time was more or less uniform for all the locations, right?
Sir, could you repeat that?
Same time of the day. Same time of the day that
data collection was same time and same month. All were considered within 30 days. All data was collected within 30 days from so annually was same time during morning after peak hour. So around 11 to 12 p.m.
Okay, fine. Okay, so okay, around 1 hour data for each of the readers.
1 hour data for each of the location, but at that time when I extracted the data from Sky automated driving extractor was not available. So I had to rely on traffic data extractor software from IIT Bombay, and I had to manually extract all the trajectories. So for amber phase, I only considered, I think, number of cycles I have provided over here as to how many I have selected. 27, 52, and 42 at these study locations. And only amber phase plus minus 3 second or 4 second data was extracted, trajectory data was extracted.
Okay, fine. Okay. Thank you. That's all.
Hello, myself Dr. Anusha from CET, College of Engineering, Trivandrum. Very nice
Hello, madam.
presentation. Yes,
Thank you.
so my concern was on the driver decision assistance system is given. So how was
Okay.
that data collected? How the communication between the leader and follower, those aspects were taken into account?
No, madam. This is what we are working on, and we are working with an assumption that it exists. Because for that, if we wish to communicate with the driver, we need support or from the local authorities so that we can install some modem so that something can be connected. And for that, vehicle and the infrastructure both needs to be modified. We are
Okay,
just
so the
working on a
15%, you were showing a figure of 15% some inferences. So was that data one
yeah,
slide
I
was
remember what this was based on, madam, model that was prepared. So we have the coefficients. So whether positive leader's decision to pass, if it is communicated and both of them adhere. Remember this, he should stop, should cross and cross, should cross but stopped. So should cross and but he stopped. So instead of that stopping, if I convert this as should cross but and also crossed vehicle, that means his decision was wrong. But assuming that he followed whatever the decision, only following vehicle adheres to the suggested decision, then what was the probability in reduction? So whichever vehicles that you see in over here, whichever ended up doing the wrong decision, if we change their decision manually to the correct decision, we found out that 11% or 15% reduction in rear end conflict probability will happen. So basically a sensitivity analysis using the model. And since that this exists, we are trying to extend it to a driver assistance system in real time.
Okay. Yeah, because I was like the data looked very nice and I was thinking how the data was obtained. Okay,
No,
I got the concept now. Yeah.
Statistical analysis, we have now that yes, this can work from statistical analysis. That yes, this measure can work provided that if the drivers are communicated. But how will we communicate the decision to the driver and when will it be communicated? This is what we are working on at present, that these are the person, this is the potential location. So we need to find out as to when then the vehicle will be in dilemma, when is the last point when they will not be in dilemma, and at that point, what was the safest decision for them to go or to stop. Please suggest that decision to continue so that they are able to cross. This is what we are trying to experiment with now. But entirely on database, madam, we don't have any infrastructure as of now.
Yes. Okay. Thank you so much.
Sure, madam.
Would anyone like to add any comments or ask any further questions on this subject?
There is a comment in the chat box.
What are your thoughts on introducing breakpoints? Breakpoints as in the small speed bumps? If the question is regarding the speed bumps, I would like to bring it to your attention that on study location 3, if you're seeing over here that I'm pointing, these yellow strips are the studs that were provided. In that study location, just before the data collection 2 months ago, there was a significant, very severe accident that took place, because of which initially, this is near Birla Temple, So initially they inserted a speed breaker, but that speed breaker was found to be very severely affecting the operational efficiency. So from that speed breaker, they ended up working with the speed bumps. But since I did not have a before or after data, I could not work with it. But the effect earlier was found to be that the dilemma zone ceased to exist because the vehicle had to decelerate to almost standstill condition from the speed breaker, and then they had to accelerate. Because of which, if it was red, most of the vehicles tend to stop, or only if the people who are either aggressive or they are in a hurry, they only went with either traffic rule violation or aggressive acceleration, but majority of the vehicles tend to undertake the decision of stopping. That was the effect of speed bump that was observed from field evaluation. What was the condition before? Since I did not know that, this thought of mine, I cannot provide you with concrete evidence. But if you want to see that accident, that is available on YouTube. Just Jaipur Birla Temple Road accident. If you check, you will see that as to why it needed such severe measure. Are there any other questions?
So now I call upon Srimati Ardra S. Krishna, Junior Scientist, to propose the vote of thanks.
On behalf of NATPAC, I would like to extend my heartfelt gratitude to each one of you for joining us today for this insightful technical talk on the topic, to go or not to go, the dilemma during the yellow phase at signalized intersection. The session has shed light on the safety risks associated with the dilemma zones. The discussion on the dilemma zone prediction and driver decision assistance system was both insightful and informative, offering invaluable solutions for improving road safety and managing the driver behavior. First and foremost, I would like to express my sincere thanks to our esteemed speaker, Dr. Ritvik Chauhan, whose expertise and knowledge have truly motivated our audience. Thank you, Dr. Ritvik, for delivering and engaging the informative presentation. We are grateful for the knowledge and insights you have shared with us today. I would like to extend my gratitude to our director and section heads and the organizing team for their kind support and in arranging this program. I would like to thank all the attendees for your presence and active involvement. The questions and discussions that followed the talk elicited your deep interest in the subject matter and are appreciated. Thank you once again to everyone involved, and we look forward to hosting more technical talk in the series and continuing this legacy. Thank you all and have a great day.
Thank you. Thank you, everyone.